Okay. Yeah. So hopefully we will finish today with the geometric realization of affine Hecke algebra. And let me draw once again this grand commutative diagram that we're going to use, or just prove its commutativity. So we have the generators, Bernstein-Lustig generators of the affine Hecke algebra. And then we have its polynomial representation, endomorphism of the induced module, and this polynomial representation. So this is the same as endomorphism of the representation ring of our torus, extended with one extra variable. So on the other hand, we have some geometric realization denoted psi of generators in terms of equivalent K-theory of Steinberg variety of triples. And this acts on some geometrically defined module, namely covariant K-theory of the flag variety. But then it's somehow the same. And let me denote this upper isomorphism by epsilon. And finally, we have some simplified version. So it's the composition of I push forward with J pull back and this psi into the covariant K-theory of just the square of flag variety, which sits as a zero section in the covariant K-theory of Steinberg variety of triples. And here you can push forward to the whole cotangent bundle and then pull back to the zero section. Okay, and here is the convolution action on the one copy of the flag variety, equivalent K-theory of flag variety. So here is just the identity isomorphism. And again, this isomorphism. So now let me recall that epsilon here in the upper right corner, it takes well, it's an isomorphism of the polynomial representation and I mean induced representation and the polynomial representation, and it induces the isomorphism of their endomorphisms rings. So the basis in polynomial representation in the induced module is given by Bernstein-Lustig generators, and then this is this almost idempotent, and it goes to just e to the power lambda. Okay, there is this sign change, and this sign change occurs many times along the way. In the definition of this psi, where the generators go, it also occurs. So we need to keep track of it. Okay, so then the compositions from the generators to the endomorphism ring in the right-hand side are denoted just psi1, psi2, and psi3. I mean, the uppermost is psi1, and the lowermost is psi3. And we want to prove that psi1 equals psi2. This is our main goal for quite a few times already. But from general properties of K theory, so it's general fact, is that psi2 equals psi3. So we need to prove that psi1 equals psi3, and this is what we will hopefully achieve today. And the point is that the square of flag variety is certainly simpler than this Steinberg variety of triples. In fact, it's a part of Steinberg variety of triples, right? Because the Steinberg variety of triples is the union of conormals to G orbits in the square of flag variety, and among them there is the open orbit. So it's conormal is just the zero section, and its closure also is inside. So it's just, so to say, the simplest part of the Steinberg variety of triples, and the calculations with it are much more manageable. That's what we're using. Okay, and in fact, the last time we already performed quite a few calculations, and let me remind the bottom line of the previous class. So first of all, there is explicit calculation of the bottom line, the rho b, in this big commutative diagram. So let me recall it. We have the following pairing. We can take the equivariant K theory of the flag variety, but only with respect to the torus. And then equivariant K theory with respect to the whole group. And it embeds into the equivariant K theory with respect to the torus both times. And then there is this pairing of taking tensor product and global sections to the equivariant K theory of the point. And this composition is denoted as trace. And then we proved this important lemma last time that about the convolution action. So we have the equivariant K theory of the square of flag variety, and here the covariance is with respect to non-extended group without dilatations, because they anyway they act here trivially. Okay, so there is this convolution action to the equivariant K theory of the flag variety. On the other hand, there is an isomorphism called restriction, because it's just restriction to one factor of this product. So it's K equivariant K theory of one copy with respect to torus, and then the same equivariant K theory of flag variety with respect to the whole group. And then there is this pairing, trace pairing. And this is just representation of T. Okay, and the point is that this diagram commutes. Okay, this is our lemma from the last time. And the last important thing we proved last time was about the geometric generators. So given a simple root alpha and simple reflection S corresponding to this root, we denote by epsilon the embedding of the corresponding subminimal orbit isomorphic to projective line into the flag variety. And then another lemma proved last time, maybe it was lemma 1. And this is lemma 2. Is about restriction. I mean, the restriction which appeared in lemma 1 over the I bar pull back, J bar push forward of the class of equivariant vector bundle that was in the definition of generators. And we computed it last time, so it was the extension from this projective line of the following difference. The class of the canonical class of this projective line multiplied by Q minus the class of the structure sheaf of this line. Okay, and also say this was part A or maybe B, and another part was that if we compute the same restriction of pull back, push forward of the line bundle O lambda, then we get just the class of the skyscraper sheaf on the flag variety at the point given by our specified Borel, and with the action of torus given by lambda. Okay, so this is a short synopsis of the previous class, and now let's use it to finish our proof that psi1 equals psi3. Yeah, and unfortunately I have to go to the next page now, and this will be not seen anymore. Okay. But well, if there are requests, we can go back to this page. Okay. So now let's compute psi3. Of theta s of TS of this generator. Okay, so by definition, this is the action corresponding to the square of flag variety over this pullback of push forward of psi of TS, just by definition. And now again, but by definition of psi of TS, this is equal to rho B pull back, push forward of minus Q QS minus 1. Okay, this is just definition of psi of TS, if you remember. Now, let's set just for notation. Say F is this pullback, push forward of QS. And then for L in the covariant K theory of flag variety, the action of our guy on L is just the trace of restriction of F tensor L. Okay, this is the lemma on lemma 1 on the previous page. Okay, this is the computation of the convolution action on the covariant K theory of flag variety. Okay, so that's what we have to compute, and then what do we get? We get that the action of pull back, push forward, psi of TS takes of lambda a line bundle on the flag variety to the trace of the extension from this projective line of negative Q canonical class plus the class of the structure sheaf minus the class of this skyscraper sheaf. Okay, tensor of lambda. Okay, and here we just use this second lemma because we know this restriction of the line bundle QS. It goes like this, and we just plug it into lemma 1. Okay, so what do we get? We get by the definition of trace pairing and the Hermann-Weyl character formula, we get negative Q global sections of this projective line with coefficients in the tensor product of canonical class, tensor the pullback of lambda, plus the class of global sections of the pullback of lambda, minus just exponent of lambda. Okay, and we only have to compute this in the polynomial representation, yeah, in the representations of torus. So this lies in here, and you see, it is the computation not on the whole of flag variety, but only on this small, tiny projective line inside. So it's really some computation for rank 1, for SL2, or maybe PGL2 or GL2, I don't know. But we have to keep track of all those equivalent parameters in the big torus, but essentially it's the question about rank 1, namely about semi-simple rank 1. So to keep track of the big torus, we have to consider this subminimal Levy subgroup. So we keep the big equivariance. So we take this Levy subgroup and extra C star, and then we take its quotient modulo its Borel subgroup. Okay, and then this quotient will be just our projective line. So L is the subminimal Levy subgroup. Corresponding to our simple root. Okay, so it's semi-simple the derived subgroup, for example, the commutator subgroup L with L will be just isomorphic to SL2. And its flag variety will be just isomorphic to P1, projective line. So its unique simple root is alpha, and say the restriction with respect to this unique simple root is just given by the usual formula, like this. So if we take the line bundle on the flag variety and restrict it to this projective line, we get just some line bundle on the projective line. It is given by just a number, and this number is the scalar product of lambda and the dual for root. And if we're interested in the global sections, then by the while Carter formula, this is the exponent of lambda. I mean, the class of these global sections is the exponent of lambda times 1 minus exponent of 1 minus lambda alpha check times alpha over 1 minus exponent negative alpha. So this is in the equivariant K theory point that equals the equivariant K theory with respect to the torus, or maybe just let me write our polynomial representation, but because it was equivariant with respect to Levy subgroup, then it's the functions on the torus invariant with respect to this reflection F. Okay. Now, what else do we need to know? We need to know that the canonical class is just O of negative alpha, and what else? I think that's it. Or maybe we also need this restriction of lambda, and this will be just exponent of lambda, the representation ring of torus. Okay, so now having all this, we can just write down what do we get, and maybe it doesn't make much sense, but maybe let me at least start. So all in all, we get the following. So we get negative Q times exponent of lambda minus alpha times 1 minus exponent of negative lambda alpha check plus 1 times alpha okay, and over 1 minus exponent minus alpha plus exponent of lambda times 1 minus exponent of minus lambda alpha check minus 1 alpha over 1 minus exponent of negative alpha and finally minus exponent of lambda. Okay, this is just the formula for this geometric expression we had in the middle of the page. Yeah, if we apply this Hermann-Weyl formula, and then if we compute it algebraically, then God willing, we obtain the desired result, namely we obtain the exponent of lambda minus exponent of s lambda over exponent of alpha minus 1 minus q times exponent of lambda minus exponent of s lambda plus alpha again over exponent alpha minus 1. Okay, and this is the end of computation of psi3. And this is the de Mazur Lustig operator. So I have announced it very long time ago. Yeah, maybe at the second class, something like this. And now finally we proved that the geometric action is given by the de Mazur Lustig operator, and this is good news. But on the other hand, we have to check it with the algebraic psi1. Okay, so this was about psi3, and now we need to compare with psi1 algebraic, and this is really simple. I mean just algorithmic algebraic computation. So let's do it. We have to compute row h of TS, say applied to theta minus lambda times E. Let's go back to this grand commutative diagram. Now we have computed the bottom path, yeah, via row B, geometric representation, and now we're computing this upper path via row H. Okay, and the basis in this induced representation is given by Lustig's element, theta lambda times E, this almost idempotent E. And we're just computing the action here, just by the generators and relations of Hecke algebra. Okay, so there was just the basic Bernstein-Lustig relation. So according to my notes, it was called C plus D, and it was, I think, in the very first class. So if you have notes, then it says that Ts theta minus lambda is theta minus S lambda Ts minus Q minus 1 times theta minus S lambda minus theta minus lambda over 1 minus theta minus alpha. Okay, and this means that the action of Ts on the element theta minus lambda times this idempotent, almost idempotent E is Ts theta minus lambda E, and this is if we just pass Ts along theta minus lambda, we get theta minus S lambda Ts minus Q minus 1 theta minus S lambda minus theta minus lambda over 1 minus theta minus alpha times E. Okay, but this almost idempotent E had the key property that Ts times E was equal to Q times E, and hence we know that rho h of Ts applied to theta minus lambda E equals Q times theta minus S lambda minus Q minus 1 theta minus S lambda minus theta minus lambda over 1 minus theta minus alpha times E. Okay, and let's denote this thing by the right hand side. So it remains to apply our isomorphism upsilon to the right hand side. So let's go back to the grand commutative diagram. You see, there is this induced module. The left ideal generated by this almost idempotent E. It has the basis of theta lambda times almost idempotent E, and it is identified with the representation ring of the torus R of T, but its identification is sort of inverse. Yeah, theta minus lambda goes to exponent of lambda, so that's what we have to apply. So let's apply it, and then what do we get? Upsilon of the right hand side is so we just change all the signs. Yeah, we take negative of everything. Q exponent S lambda minus Q minus 1 exponent of S lambda minus exponent of lambda over 1 minus exponent of alpha, and then this is well easily transformed into the desired form, namely exponent of lambda minus exponent of S lambda over exponent of alpha minus 1 plus q times exponent of s lambda plus alpha minus exponent of lambda over exponent alpha minus 1. And this is just what we wanted. So it again, the same Dimash-Lustig operator. Okay, so this is the happy end of the big proof. So we can start an isomorphism from the affine Hecke algebra to the equivariant K-theory of the Steinberg variety of triples. Okay. So congratulations. And now let's have some applications of this geometric interpretation. But let me just say a few words before we move to applications, because we used quite a few basic properties of the equivariant K-theory, and I don't want to go into the proof of them right now. I want to delay it to December maybe. So first we'll derive some applications and then return to the foundations of K-theory. But just maybe let me list these basic properties we used. Oops. Sorry about this. What do I do? Oh, very simple. The list of basic properties. Of equivariant K-theory. So to say, my debt to you, maybe till December. Or maybe till next life. So what did we use? We constantly used the cellular vibration lemma, computation of K-theory of union of cells, like flag variety or even the Steinberg variety. In fact, any variety we used was like this. Okay, then we used the Skewnit formula. Then we used the Thomason localization or concentration theorem. And then we used that the homomorphism from the map from the equivariant K-theory of the Steinberg variety of triples into the equivariant K-theory of the square of flag variety, given by the pullback of push forward, was a convolution algebra homomorphism. So it takes convolution to convolution. Okay, and I think this is more or less it. These are 4 basic properties. Okay, and hopefully we'll have time to get back to them. But if not, you can just look them up by yourself in Chris Ginsburg. Okay, so they are in the early chapters, and they do not you use anything else. Okay, so now let's move to applications, that is representations. Of the affine Hecke algebra. And you see, the representations will be certainly over complex numbers. And I mean, up to now, this affine Hecke algebra was an algebra over the Laurent polynomials in Q, but with integral coefficients in Z, right? But since we'll consider complex representations, we might as well complexify the Hecke algebra itself, or C representations of our Hecke algebra. We will use the complexification H tensor C over Z, and somehow I will just keep the same name. So we will never again use this integral form of Hecke algebra. We will only use complexified one. So from now on, H will denote the complexified one. Okay, and then recall that we computed its center in I think in the second class. The center of H was isomorphic to the well, let me say it this way. It was the representation ring of torus W invariant, and now I have to complexify it, and there is also one extra parameter, and this is the same as the representation ring of our extended group, but again complexified. And this is the same as the ring of invariant functions on our extended group, invariant with respect to conjugation. Okay. Now the spectrum of the center is the set of semi-simple conjugacy classes in our extended group, and say given an element A, we write it in the following form. So here S will be semi-simple conjugacy class, or semi-simple element representative in G, and T will be an element in this extending C star multiplicative group. And then given such a point, we can consider the corresponding one-dimensional module over the center. Well, denoted CA, just one-dimensional module over the center. Okay, and we will denote HA will be the tensor product over the center with this one-dimensional module. Okay. Now recall that our Hecke algebra was free module over the polynomial ring of torus of rank equal to the while group, and in turn this Bernstein subalgebra is a free module over the center of rank, again, the order of the while group. And hence, this H alpha is finite dimensional algebra of dimension W squared. Okay, and we'll study representations of such algebras. But first, let me explain that in order to classify irreducible representations, that's enough. So it's sort of sure lemma. That if M is an irreducible H module, then Z of H acts on M by a character A for some A, and hence the action of H factors through this quotient with a reduced central character HA. Okay. Now let's prove this lemma because it uses my favorite trick by Amit Sur. So I'm also giving course in basic algebraic geometry these days, and there we also use this Amit Sur trick. So I'm very fond of it, and I try to use it anywhere I can. So the point is that the endomorphisms over H of this irreducible module is necessarily a skew field. I mean, every non-zero endomorphism is invertible. Yeah, that's clear. That's the usual sure lemma. But now we know that the dimension of this Hecke algebra over complex numbers is countable. Yeah, we will know this Bernstein-Lustig basis, for example, or the standard basis. And hence, the dimension of this reducible representation over complex numbers is also countable. And there is some expression for this, but I mean, it's aleph not, but I've always forgot. I always forget how to write this aleph. So it's maybe I'd better not try. It's just countable. Okay. I mean, you take just any non-zero element, right? And then you act by the basis of Hecke algebra on this single element, and it certainly spans the whole module by irreducibility. Okay, but then again, by irreducibility, it implies that the dimension of endomorphisms over Hecke algebra of M is countable. I mean, because the whole module is generated by a single element, H goes to H of M is an embedding from endomorphisms of M into M itself by irreducibility. Yeah, everything for a generator M. Okay, so anyway, this endomorphism ring has countable dimension, and now this Amitsur trick says that any skew field over C of countable dimension is just C itself. Okay, because otherwise for any transcendental element T not in C, the collection of elements T minus some constant inverse is linearly independent. Okay, so here C runs through complex numbers. So this is the proof of the Schur-Amitsur lemma, and we know that all irreducible representations of the affine Hecke algebra factor through those finite dimensional W² dimensional quotients with a reduced center with a particular central character, and we only have to study those. Okay, so the rough, the first part of classification, the rough part according to central characters, is already achieved now, and now given a particular central character, yeah. So recall that A is a pair of elements, semi-simple element of our group G, and an element of the multiplicative group T. We want to classify the finitely many irreducible representations of this finite dimensional algebra HA. Okay, this is our goal for November. Okay, so from now on, we will study irreducible representations of this finite dimensional algebra. Okay, so to this end, we'll introduce another geometry, namely the fixed points of the Steinberg variety of triples. Okay, and just by definition, this ZA, the fixed point set, is again the fiber product of the fixed point set in the cotangent bundle to the flag variety over the fixed point set in the nilpotent cone. And the cotangent bundle to the flag variety is a smooth variety, so its fixed point set is also smooth, and so it's in a sense similar. We take the Cartesian product of two smooth varieties over some non-smooth base, so we obtain something maybe intimidating, but at least it lies inside the smooth variety like this. Okay. And we can consider its K-theory again. Now it's not equivariant at all. Yeah, there no equivariance left.
Миша,
Yes.
я прошу прощения.
Да.
У тебя здесь А элемент группы, да?
Oh, yes.
Сейчас. А нижний индекс А в записи error HA это не элемент группы или
No, A is a fixed semi-simple conjugacy class. Or I can think of it in terms of its representative. So I fix a semi-simple element in G, just a number T, and there I am.
Сейчас, просто секундочку. Вот я, наверное, просто прослушал. Когда мы говорим про вот это HA, мы говорим про такую центральную редукцию.
Oh, yes. Absolutely. Yes.
Центр там это инвариантные функции.
Invariant functions on G. So the spectrum of invariant functions on G is the categorical quotient of G modulo G, but the points are well, conjugacy class of semi-simple elements.
Да, все, прошу прощения.
I mean, they are closed orbits, but the closed orbits are semi-simple orbits, and we discussed this a year ago, or half a year ago in the invariant theory class. Okay, so we want to consider this variety, and we will start with the following theorem, that HA is the convolution ring of K-theory, but not equivariant anymore, of this fixed point set. Okay, but complexified. And also it is, well, maybe isomorphic. Also it is isomorphic to the convolution ring of Borel-Moore homology of this thing with complex coefficients. So these are Borel-Moore homology. Okay, and this is, so to say, rational or additive analog of K-theory. I mean, coherent K-theory of K group, well, K-theory, and this is in turn trigonometric or multiplicative analog of Borel-Moore homology. Okay. I mean, those words are rational or trigonometric, additive or multiplicative. Well, additive and multiplicative is maybe more geometric, but rational or trigonometric, it refers to the corresponding algebras we obtain. So I will now proceed to explain what are those Borel-Moore homologies, just by definition. But before I explain this, let me say that we could play the same game from the very beginning. I mean, I could consider the equivariant Borel-Moore homology of the whole Steinberg variety of triples. So I could take the equivariant Borel-Moore homology with respect to the same group of the same Steinberg variety of triples, and this will be the rational analog of H, and it's called the degenerate or graded affine Hecke algebra. H degenerate. Okay, and it is not isomorphic to the Hecke algebra proper. I mean, this Hecke algebra has some filtration, and the associated graded of this filtration is the degenerate version, the graded version. Okay, but so let me write it down. H degenerate is the associated graded algebra of the affine Hecke algebra, and it's not surprising because the Borel-Moore homology has just the grading by degree, and it's compatible with multiplication, so it should rather be this way. It's fine, but still they are not isomorphic. But as you see, the representation theory are identical for the degenerate version and for the whole version. So after you pass to any particular central character, the reduced algebras are already isomorphic. Okay, so H degenerate, so to say, logarithm A will be isomorphic to H. Okay, and somehow this is sort of a general principle that persists through many representation theories. For example, if you take instead of Steinberg variety of triples, if you take Nakajima-Quiver variety, then in place of affine Hecke algebra, so in K theory, you will get some quantum affine algebras. Yeah, the quantizations of universal algebras of affine Lie algebras. And in place of the degenerate version, you will get certain Yangians. And again, as algebras, Yangians and quantum affine algebras are not isomorphic by any means. But representation theory, the finite dimensional representation theories are identical for the same reason. Okay, and now I have to give a rigorous definition of Borel-Moore homology. So I will not give a definition of equivariant Borel-Moore homology. So we will not define this big degenerate affine Hecke algebra because it uses some more advanced derived category techniques. But I will only consider non-equivariant Borel-Moore homology for these small algebras. and that'll be enough for our purposes. The advantage of this Borel-Moore homology still is that they can be defined in various ways, in particular in a sheaf-theoretic way, via some constructible sheaves. So it's essentially a cohomology with coefficients in dualizing sheaf. Then this approach to Borel-Moore homology has very big advantages over K-theory. Namely, if you realize it in sheaf-theoretic way, you can use some localization technique. For K-theory, it's unavailable. There is only, at least till recent times, it was unavailable. Now the people start thinking of K-theory as cohomology, so to say, with coefficients, some sheaf of what spectra of K-theory, and then the localization also becomes available. But before recently, it did not work this way. So the Borel-Moore homology is much more soft, so to say, and the K-theory used to be much more rigid. Well, we'll see during November how it works, how the Borel-Moore homology approach allows to use some sheaf results and classify the finite dimensional representations. Okay, so let's go to the formal definitions. So the definition is as follows. We have some topological space. And this is the reduced homology of the one-point compactification. X hat. Okay, and also, if you have any other compactification, then still you can take homology, but I mean, in the ordinary sense, as opposed to Borel-Moore homology of this compactification modulo the boundary for any compactification. Bar. And also, this is some advanced point of view. This is H, the cohomology, but with the degree negative, with coefficients in the dualizing sheaf. Dualizing constructible. Complex on X, and then by the sheaf theoretic Poincaré duality, this is the same as the cohomology with compact supports and with coefficients in the with usual constant complex coefficients dual. Okay. Okay. So now I will proceed to some basic properties of Borel-Moore homology, and to some extent we'll be able to stick to this basic pedestrian definition as the reduced homology of one-point compactification, but for many properties we'll have to use this realization as cohomology of the dualizing sheaf. Without it, we'll not be able to construct the morphisms we'll need. Okay, so here is the list of properties. So first is that if you have a proper morphism, then it gives rise to the morphism of Borel-Moore homology. Just because since pi is proper, the pi bar from the one-point compactification of x to one-point compactification of y is continuous. Okay. Now the second property is a long exact sequence. So if u in x is open and the complement is z closed, then we have a long exact sequence. Some homology of z goes to homology of x, goes to homology of u, and then goes to minus first homology of z, and so on. Okay, how does it work? So we have some morphisms in this long exact sequence. So for example, how does the restriction morphism from x to the open work? We know that the homology of x is the ordinary homology of some compactification modulo the boundary, and it goes to the ordinary homology of the same compactification, but modular complement to u, and this is the Borel-Moore homology of u. Okay, and this is for restriction from x to the open subset u, and for the rest, let's embed x into a smooth, compact manifold M. And then the Poincare duality says that the Borel-Moore homology of x is isomorphic to certain cohomology of this ambient manifold modular the complement, and the same for z. So here M is certainly dimension of the ambient manifold, and the same for U, and then the above long exact sequence is just h k of M modulo M without z goes to hk of M modulo M without x goes to hk of M modulo M without u goes to hk plus 1 of M modulo M without z, and so on. Okay. Now, the third property is that a smooth oriented variety X, or manifold X, has the fundamental class in the top homology, so it's dimension of X. But then, well, it's a real variety, so dimension over real numbers. But mostly will have complex varieties, so the dimensions will be doubled. Okay, and if X is now a complex variety and say irreducible, but mind that it's only a variety. Yeah, it's not necessarily smooth as opposed to before, and not necessarily compact. So we have the smooth locus, and the complement has a real codimension at least 2. Okay, and it from the previous part 2 exact sequence, we have that well, first we know that the Borel-Moore homology of the singular part vanishes in degrees bigger than twice complex dimension of X minus 2, and then from this exact sequence, we get that the in this top degree twice complex dimension of X, the homomorphism to the top degree homology of the open set, smooth locus, is an isomorphism. Okay, and the smooth locus does possess the fundamental class, as we discussed in the beginning. Okay, so any reducible component of top dimension n has in fact, I don't need any, how to say it. Okay, a little bit top dimension n. It has a fundamental class. The fundamental class xi. Okay, and it lives in the 2n homology of X, and they form a basis in this top homology of X. Okay. Okay. Now the next property. In case M is a smooth oriented manifold, no, real manifold, and Z and Z prime in M closed subspaces, not necessarily smooth, and then in this situation there is a sort of intersection pairing. Ith Borel-Moore homology of Z times jth Borel-Moore homology of Z prime goes to H I plus J minus M homology of intersection. Here M is the dimension of the ambient manifold, and this is Poincaré dual to the usual cup product. Cup product H M minus I of M modulo complement to Z times H M minus J cohomology of M modulo complement to Z prime, and the product goes to H to M plus, minus minus I minus J over M modulo M minus 1 guy union with M minus the second guy. Okay. Now the fifth property is Q-net formula. That the external tensor product is an isomorphism from homology of X1, tensor homology of X2 into homology of their product. Okay, now next property is a restriction with supports. So suppose we have a smooth embedding iota from X to Y. Of oriented manifolds, and D is the codimension, and Z in Y is a closed subspace. And then there is this pullback restriction with supports from the Borel-Moore homology of Z to the Borel-Moore homology of its intersection, but the degree drops by this codimension, namely C goes to the class C goes to its cap product with the fundamental class of X, and it's Poincaré dual to the restriction cohomology of y modulo the complement to z to the cohomology of x modulo the complement to intersection. Okay, and now the compatibility with what we had before is that if we have two classes, z and z, two subspaces in an ambient manifold, and we have two classes, c and c prime, in the cohomology of z and cohomology of homology, Barrel-Moore homology of z prime, then the cap product of two classes is the diagonal restriction of their external product. Okay. Now maybe I'll have time for one more. Smooth pullback. So suppose I have a morphism from x to y that is an oriented bundle with a fiber f. Okay, but x and y are not necessarily smooth themselves. But the vector, but the bundle is smooth. Yeah, so this fiber f must be smooth. Okay, but the total space and the base are not necessarily smooth. Okay, and under these circumstances, we have a pullback p upper star from ith homology of y to I plus d homology of x, and again d is the dimension of x minus dimension of y. Okay, and now to formulate this, I mean to explain this morphism, I need to use this advanced definition of Barrel-Moore homology. So this is due to the fact that if we take pullback of the dualizing sheaf of y, this will be the dualizing sheaf of x up to the shift in homological degree. Okay, and one last, or maybe let me just stop here. Let me stop here and continue with this property next time. So let me save this note file. Let me stop the recording.